Hello, and welcome to Solar Alberta's 2025 Solar Series. Today's session is called Beyond Roof and Ground Mounts, Intro to Building Integrated Solar. We were delighted to have so many people register for this event. Please note that we will be recording this webinar for future distribution. The recording will be emailed out to all those registered and posted on our YouTube channel after it is edited. My name is Heather McKenzie, and I'm the Executive Director of Solar Alberta. I'd like to take a minute to acknowledge that I'm hosting you today and working day to day from Amiskwaciwaskahigan, also known as Edmonton, Alberta, Canada, located on Treaty 6 territory and the homelands of the Otipemisiwak Métis Nation. Treaty 6 territory is a traditional gathering place and home of many Indigenous peoples, including the Papachase, Nehewak or Cree, Saulteaux, Dene, Blackfoot, and Nakota Sioux, nations whose ancestors have cared for and nurtured these lands since time immemorial. Today, we'll be hearing from Adam Yereniuk from Kubi Renewable Energy and Sydney Browne from the Diamond Schmidt Architects. Following their presentations, there will be a question and answer period in which you can all participate. The entire session will wrap up in an hour and a half. Please note that we have enabled closed captioning for this presentation. You can turn the captioning on in the toolbar at the bottom of your Zoom screen. During our Q&A period, we will be using Zoom Q&A for questions rather than the chat box, so please enter your questions in the Q&A section. Also, please click on the little thumbs up symbol to upvote questions that you like. Now I'm just going to share a little about Solar Alberta. Solar Alberta is in its 34th year of operation. We're a nonprofit society that is dedicated to accelerating Alberta's transition to a just and sustainable energy future. We do so by advocating, educating, and serving as an industry and community hub for solar energy. Our membership is made up of over 200 individuals and more than 150 businesses. We also have more than 33,000 followers. We provide a number of services, including managing a solar directory through our website. In this way, we act as a bridge for installers, suppliers, and other solar-related businesses to connect with their customers and clients. Our directory gets more than 26,000 hits every year. You can also see a link to it in the chat. We run a number of educational programs, including our Solar Series webinars and workshops. On November 19th, we're hosting an industry-oriented morning webinar called Alberta's First Virtual Power Plant. That will be our last event of 2025, so don't miss it. Registration for November 19th is free and can be completed through the link in the chat. You can also see free archived videos of all our previous webinars on our YouTube channel. Just a reminder to save the dates of January 27th to 30th for our 2026 Solar Show. This is our 4-day virtual solar conference. We're going to be featuring seminars for the general public, solar enthusiasts, solar installers, solar developers, green builders, and more. Be sure to check back on our Solar Show page and watch our social media channels as we announce the speaker lineup. Registration for most of the sessions will be free and will soon be available through the link in the chat. In addition to our webinars, we have a number of affordable online courses for solar industry professionals or those transitioning into the sector. Most of our courses are online on Tuesday and Thursday evenings. Next up is Navigating Alberta's Electricity Grid, and that starts on Tuesday, October 21st. We're once again offering our solar training course bundle. This bundle includes our 4 technical courses for the price of 3. The link to purchase the bundle and all of our courses individually is being placed in the chat. On-demand recordings of our courses are also available for sale alongside affordable industry-oriented webinars in the solar training section of our website. In addition to providing education about solar, we also advocate for it. We are currently rising up for renewables with a municipal election on Monday and candidates out in your community. There's no better time to signal your support for renewables. We have free lawn signs available for pickup in 10 municipalities, and we offer free delivery in 8 municipalities around Alberta. We also have template letters for you to use on our website asking the Government of Alberta to eliminate the discriminatory buffer zones that they have established for renewable energy. You can click on the link in the chat to make a free sign order or find a template letter today. We're also placing a special new link in the chat to a solar report card initiative we just launched at the end of September. For the first time ever, we have compared and contrasted how solar-friendly various municipalities are around Alberta. If you live in one of Alberta's major cities and are curious how your municipality is doing on adopting solar-friendly policies, please click on the link in the chat to view our report cards. We'd also love your help circulating these report cards over the coming weeks to ensure that all those who run for or elected to municipal office have solar on their mind. Lastly, if you're not already a Solar Alberta member, I just want to encourage you to join. Individual memberships are only $35 and you get access to a variety of benefits, including discounts on courses, workshops, access to member-only newsletter and website content, and more. If you're looking to support the work that we're doing in additional ways, you can also consider volunteering or donating. I'd like to take this opportunity to thank LMX for sponsoring today's webinar. We couldn't offer all of this amazing free content without the support of our sponsors. We are always interested in developing more partnerships for our events. If you or your organization want to work with us to educate the public about solar or solar-related technologies, please don't hesitate to reach out. Now, without further ado, I'd like to introduce our session sponsor, Tyler Key from LMX. Tyler's going to tell you a little about LMX and then introduce our two speakers for the day. Welcome, Tyler, and thanks for joining us.
Thanks, Heather. Ladies and gentlemen, on behalf of the team at LMX, I'd like to welcome you to this webinar. I'm Tyler Key, Regional Sales Manager for Western Canada with LMX based out of Red Deer County. LMX is a Canadian firm providing tariff-free Canadian assembled building integrated photovoltaic facades. We offer unmatched design flexibility with up to 17 standard colors and the widest variety of panel sizes available today. All of our architecturally engineered facade solutions connect to buildings with an integrated pressure equalized rain screen. Utilizing our Unity platform, you can attach a variety of external facades, including but not limited to solar, vandalism-proof sintered ceramic, fire-resistant aluminum plate, or even standard ACM panels. These alternatives are excellent at grade where solar panels could be damaged, or on the north sides of buildings where power generation is not ideal. We've got the entire building covered. LMX works with a sales rep agency, Pilot Group, based out of Calgary. Pilot Group has over 20 years in the building envelope industry, making them a valuable partner to architects, designers, and contractors alike. Pilot Group offers LMX training sessions for various professional organizations across the prairies. If you're interested in having a presentation in your office, please don't hesitate to reach out to me directly or the Pilot Group. LMX is particularly pleased to be sponsoring an event with both Adam and Sydney today. If you're interested in our solutions at LMX, architectural professionals like Sydney can build them into her beautiful designs. Expert solar installation professionals like Adam can have his team install them on your building. We're really looking forward to the experiences that Sydney and Adam will share today. If, after this presentation, you're interested in investigating architecturally designed, building integrated photovoltaic facades, we would welcome the opportunity to help you harness the energy of the sun in your next project. Check out our website at www.lmx.com. I'd like to introduce to you Sydney Browne. Sydney Browne studied architecture at the University of Waterloo and University College Dublin. She joined Diamond Schmidt in 1999, and as a principal, she has led and contributed to many significant cultural and academic projects constructed across Canada. Sydney is passionate about design and its ability to affect positive social change and foster well-being in environments where we live, work, and learn. Her work has included projects designed to lead in Green Globe's mandates and has been recognized through numerous awards for sustainability, design, and innovation. Current projects include at Asoke, the new joint facility for the City of Ottawa and Library and Archives Canada, where Sydney's leading Diamond Schmidt's design team in pursuing the CAGBC's Zero Carbon Building Design designation. Adam Yereniuk. Adam Yereniuk is the CTO and co-founder of QB Renewable Energy, a solar PV engineering, construction, and procurement firm in Alberta and British Columbia, with offices in Edmonton, Calgary, Lethbridge, and Kamloops. Adam oversees all technical aspects of QB and is QB's principal professional engineer. QB has been involved in several large-scale BIPV installations in Alberta, including Red Deer Polytechnic and the Edmonton Convention Centre. Since 2015, QB has installed more than 5,000 residential and commercial microgeneration systems in Canada, totaling over 40,000 kilowatts. I will now pass the microphone over to Sydney to begin her presentation.
Thanks so much. So as Tyler mentioned, I'm an architect and a principal with Diamond and Schmidt. I'll just share a little about our firm. Our firm is a group of over 300 architects. We have studios in Vancouver, Calgary, Toronto, and a group in New York. And for our firm, environmentalism and energy are significant design issues. And as you see here, we've developed a fairly robust expertise in various aspects of sustainable design. For our team, the tracking of what we're able to achieve in terms of energy metrics for all of our projects is a constant pursuit, constant passion. And within each one of our projects, as in the handful of Alberta projects that you see on the screen now, we're always interested in trying to get at the combination of green building measures, sustainability considerations that are the best fit for each one of these projects. And that path has taken us in a number of directions over the last 2 decades. But the group of projects that I'm going to speak to you about today are selection from the handful that you see on the screen. We've been working with photovoltaics, building integrated photovoltaics as part of our design work for some time, and over the last decade, we've learned a lot and continue to learn through each one of these projects. So I'll take you through a handful of these projects. I'll go fairly quickly, but at the end of my presentation and Adam's, we'd be certainly happy to go through questions you may have. To begin with, a little more than 10 years ago, we started working with Sifton Properties to develop first their head office in London, Ontario, and then to work with them on a number of other aspects of PV installation as part of the net zero community that they have been developing for some time. So this project is their head office, and really based on their initial interests in solar and on-site renewable energy, we began to develop this cladding system, which incorporates industry standard PV panels. I'll just pause for a moment and explain that BIPV, building integrated photovoltaics, are, I think, distinguishable from earlier applied photovoltaic systems in that what we're beginning to work through are integrated solar systems. So rather than just taking solar components and applying them to a building construction, what we're looking at are the opportunities to incorporate photovoltaics as an integrated part of the building cladding system. So in this case, the project is part of the exterior wall envelope, and I'll take you through others that look at different components that are integrated within a building envelope. So this project made use of standard components as part of the exterior cladding system. And as a continuation of our work with Sifton, we then went on to work with them on this multi-unit residential building. And you can see on the facade of this building and the adjacent parking structure, the facade in both cases incorporates standard PV panels. And what we're doing in both of those, or what we were doing, was taking the kinds of panels that you see installed on the roof of those projects and looking at ways to incorporate those as part of the exterior cladding system. So taking the vertical the vertical plane and developing it in a way that is relatively consistent with what's being done on the roof. But whereas the roof system on the left is added on top of the exterior roofing membrane, what you see on the facade on the right is starting to take these panels and integrate them as part of the exterior cladding system. The challenge here was to take these standardized, repeated modules of fixed dimensions and to begin to develop a series of details that could take those standardized panels and start to adapt them to the customized detailing that is required as part of a more integrated building facade. At that point, we started to look at other opportunities for incorporating photovoltaics within building construction, and our next test installation was through glazing, exterior glazing, through one of the exterior window systems that you see on this project. This is the Canada Science and Technology Museum in Ottawa, and here we were looking at taking another product, Spanish glass, that incorporates photovoltaic cells as part of the exterior glazing. Again, just a test installation and not as fully effective in terms of output as the cladding, but we felt certainly worth installing as a test case in this scenario. At this point, we're very fortunate to take on a commission with Red River College Polytech in Winnipeg. And for this project, their innovation center, and the college was really interested to see what could be done to develop a much more innovative approach that took energy use very seriously in an integrated way. And so this project was targeting an energy use intensity of 100 kilowatt hours per meter squared per year, as well as LEED Gold. And this idea of making a much more holistic, integrated, energy efficient project began to lead us in a number of directions explored throughout the design process. So you see here a map showing the photovoltaic power potential across the country, and as you can see, Winnipeg is on the periphery of the most, as part of central Canada, one of the most beneficial in terms of long-term, year-round PV potential because of exposure to sunshine. So this we felt was a really promising starting point in terms of looking at incorporating PV into this project. The site that we were given is located in the center of Winnipeg, downtown site with an existing factory building on one side of the site and a sort of standard urban condition with buildings on most sides of the site. The project included retrofit of an existing heritage warehouse, as you see on the right-hand side of the screen, and there we had the opportunity to incorporate rooftop photovoltaics. And on the left-hand side of my screen, you can see new construction, which allowed us greater opportunity to include rooftop PV, but also to begin to explore opportunities for facade integrated photovoltaics. The project that inspired some of this work that we became aware of at this time is the Copenhagen International School that you see on your screen. One of the first European projects to incorporate a custom approach for solar facade panels as part of the facade construction. And in this case, the facade panels are simply like the Sifton project that I showed you earlier, are simply attached to a more integrated or more complete exterior insulated metal wall panel system. So we were very interested to see the potential of this system and visited the project. And for the Red River project, we started to look at what would be involved in taking on this kind of system, but really adapting it to a Canadian context where we develop rain screen systems, as Tyler mentioned, as part of our sort of fundamental approach to building facades. So the glass that Solar Lab, the Danish company, brought to us, the company who was involved in the design and fabrication of the Copenhagen project, as you see here, brings a whole new range of opportunities for color variation, customization of panels, and at the same time, through the construction of these panels, incorporates the same solar cells within the body of each one of these panels. So taking that standard approach, as you see in the commodity panel systems, but beginning to look at what can be transformed in terms of appearance, in terms of size and customization. So the system that we developed, working closely with Solar Lab, you see here shown in kind of simple diagrammatic form. The interior and backup wall construction is similar to what we would be looking at in most Canadian construction projects, backup wall, insulation, sheathing, air barrier, and so forth. But added to the exterior component, our cladding is made up of a special glass panel that includes this nano coating on exterior glass, a series of integrated photovoltaic cells sandwiched behind that glass, and then a backsheet and backup framing that allows us to provide a customized exterior cladding system with room for junction boxes, cabling, and so forth on the back side of the facade. So this is a diagram showing essentially the way that system is put together. What you see on the screen now is the finished project. The building in the right foreground is the restored and refurbished Heritage Warehouse, and the larger building beyond with the gold cladding and the colored roof awning is the new construction. And what you see shown in gold is the PV cladding. In order to develop this system, there was a whole series of steps worked through with Solar Lab and our construction manager, small-scale mock-ups for the construction industry and local building authorities, larger mock-ups developed on site in Denmark to test the assemblies at a larger scale, and eventually moving to mock-ups on site. And what you see here is the backup wall construction, which would be part of a typical rain screen construction, including air vapor barrier, insulation, seagirts, and so forth. And then the first of the custom PV panels installed on site. So that's gives you some sense of the way that the facade is put together, and ultimately this is what that exterior screen, rain screen, looked like. In order to develop this process and ensure that we were getting the output that the college was looking for in terms of energy effective construction, we went through with our team a lot of modeling throughout the development of the process. And you see in this diagram a series of steps worked through as we progressively looked at ways to improve the energy efficiency and overall performance of the system. And part of that process required at a certain point that we begin to look at on-site renewable energy. So we looked first at rooftop photovoltaics, and working with SMS, our electrical engineers from Winnipeg, there were studies done to consider the orientation of roof panels in order to maximize the output. And then eventually looking in a more refined way at the optimal tilt for the roof panels. Working with PV panels on the roof, however, was not enough to give us the energy output that was targeted for the project. And so at that point, we also began to look at what could be developed in terms of building facade photovoltaic cladding. And as you see here, in the diagrams on the right-hand side of the screen, yes, there's a lot to be gained through angled rooftop photovoltaics, but there's also a significant benefit we found through early modeling to incorporate photovoltaics as part of the cladding for the exterior envelope. And in adding that rooftop photovoltaic and cladding component, we're able to take the overall EUI demand of the building, which was still just a nudge over 100, 112, adding then the opportunity for PV generation and the resultant combined performance falling well within the 100 EUI target. And the end result of that is cladding and rooftop PV that provides overall close to 20% of the electrical energy required in the building overall, and has contributed significantly to LEED Gold construction for the project as a whole. The project is now LEED certified. And the project was, I think, successful in many respects. And one of the ways that was recognized was through the Canada Green Building Council Award for New Construction in 2023. And one of the reasons they recognized the project was the cladding, which incorporated photovoltaic glass, first of its kind in Canada at that time. I'll just move very quickly on to a second project. As we were so encouraged by the success of the Winnipeg project, but we knew that it was in one of the sunnier areas of the country, and we wanted to test out what the opportunity was for similar systems in other parts of the country. So the next project where we took this on was through the Innovation Village project for Fanshawe College in London. And as you see here, the site is located in the center of an existing college campus with buildings on all sides. We knew, however, that even with buildings around us, because of the height of this building, we had an opportunity to test out this cladding system. We knew from cost studies that the custom photovoltaic cladding was well within the range of the types of cladding systems that we would be looking at for similar quality construction in this market. And we're very interested to test out what could be gained through energy production and what value that brought to the site. So what you see here are section details for this building. It's quite similar in a number of respects to the Winnipeg project, but we started to investigate tilting the facade panels in order to improve performance. You see a detailed photo of the results and a photograph of the building overall. So this has been up and running for a period of time. As I said, we're very interested to understand the performance of these systems. And in this project, there was serious attention given to the benefits of putting PV on all sides of the project. And so this diagram shows the schematic layout of BIPV panels on all four sides of the building. And early modeling suggested that this was a viable approach. And this has been borne out in the demonstrated data tracking that has been available to us since the project has been in use. What you see here is a really simple diagrammatic markup for 1 month, just looking at each color band to try to track the output for each facade. And you can see a color assigned to each one of the building facades. And the orange band, as you can see, is well in the running in terms of the output generated for each one of the facades of the building, and clearly demonstrated to our team and to the college the benefits of looking at PV on all sides of the building as part of an integrated facade approach. This has also been borne out in some of the initial data coming out through our commissioning studies for the project. The first 8 months of commissioning data identified, as you see here in green, and the output from 1 month to the next of the electrical energy demand that is generated on site compared to what is required on site. So going from month to month, in the month of August, roughly a quarter of what the building needed was provided on site. But as we move into the cooler months, the shoulder season of September, October, November, you can see that close to 100% in some months of what the building requires is provided on site. And then as we move into the winter, that number starts to drop in December and January. But then again, in February, as the days become longer and the weather warms up, the building is able to provide more power on site. And overall, as an average across those 8 months, the facade of the building generated just over 60% of the electrical energy demand that was required within the building, which is a truly remarkable performance, particularly in this area of the country where we don't have the same benefits of long sunshine hours. So those are two projects in particular that we've looked at, but I just wanted to give you a quick sense of other work in progress. The last two projects I showed you were primarily new construction, but we're also seeing huge potential in terms of deep energy retrofit, as in this project for the region of Peel, where we're working with them to look at replacing and upgrading, expanding windows and recladding the building, retrofitting interior systems to electrify the building as a whole. And the results of this are demonstrating in modeled form that we're able to cut the building EUI from somewhere over 300 kilowatt hours per meter squared to close to 100. So really significant improvements as part of the deep energy retrofit, and significant contribution to that comes through overcladding with BIPV. Tyler had mentioned one of the projects we're involved with is at Asoke for the Ottawa Public Library and Library and Archives Canada. This project is under construction now. It's connected to a district energy system, and is our first combination of renewable on-site energy in combination with a district energy system. So this is targeting a zero carbon design, and well on its way. Just recently, we've opened the Barrie Bus Terminal, where a building integrated photovoltaic canopy is providing all of the power required to operate the adjacent bus terminal. This is the first project we're working on where we're able to start to look at feeding back into the grid. And then lastly, just one more project, the Myron and Berna Guerin Health Sciences Complex, a new medical school in Ontario, where for the first time we're able to work directly with a Canadian manufacturer of building integrated PV panels. And this project, again, well on its way. You can see the mock-up in the photo on the left. So these projects are learning opportunities for all the members of our project team. And I just wanted to close with a few comments. First, I'd say that every one of these projects is its own set of conditions, and the solutions that we look at vary considerably from one project to the next. But fundamental to all of these is the idea of teamwork. Because this is a new approach to construction and new technology, often involving trades and construction partners who do not normally work together in close partnership, teamwork is an essential part of any one of these projects. I'd also add that while it's maybe sometimes brings new working relationships for our team, it also brings new working relationships in terms of requirements for testing at multiple stages, for working with the authorities having jurisdiction. And ultimately, this is a learning process for all members on the consulting team side, but it's often something that's new for the authorities we work with, and working closely with them is a necessary part at each stage of these projects. Once they're in place, though, while the project that leads to construction can be more complex, it for certain is more complex and requires extra effort, the end results are remarkably simple and remarkably productive. When we think about all of the mechanical components that make up many of the building systems for these projects, which you see identified on the right, the simplicity of the photovoltaic cladding systems is remarkably dependable, remarkably productive, and we see huge value in continuing to work with the combination of these systems. I'd also say, just in closing, we're learning as we go, but I think we're part of a whole industry that's learning, and there are more and more resources available all the time. The Building Integrated Photovoltaics Technical Guidebook that you see here is now available to all online. We're happy to have both the Red River and the Fanshawe projects included within that international publication, but there are a number of really valuable resources and some great information available through this guidebook. And additionally, I would say through evolving national standards, CSA has been developing a series of updated standards for PV components and BIPV over the last 2 years, which is an important part of this evolving industry. So I'm going to pause here. As I said, this is just part of the work we've been doing over an extended period of time. We learn with every project, but one of the things that stands out most is the enormous potential with this technology, and we're happy to share what we know. So at this point, I'm going to pause and I'll ask Adam to take over the screen.
Hello, and thank you very much, Sydney. My name is Adam Yereniuk, and I am the CTO and co-founder of Kubi Renewable Energy. I'm a professional engineer, and I'm going to talk to you about our experience with a couple of BIPV projects here in Alberta, the Red Deer Polytechnic Residence Building and the Edmonton Convention Center. I'll touch on some of the technology available, and then I'm going to dive into some financials at the very end. First, Kubi Energy, we're a solar power engineering, procurement, and construction firm specializing in residential and commercial solar power and battery energy storage systems. We are one of the largest solar contractors in Canada, and we have four offices across Alberta and BC. To date, we have installed around 40 megawatts, roughly 5,000 solar PV systems, and we've been around for about 10 years. We're an experienced team that's been through multiple technology, government, and economic shifts, and BIPV is one of the upcoming trends in photovoltaics. So let's jump into some projects. This is Red Deer, excuse me. This is Red Deer Polytechnic Residence Building. Now, everything you see here is a photovoltaic panel. All of the black, rather, is all photovoltaic cells. So this job was the architect behind it was Reimagine, which is formerly Manask Isaac. I believe it was built by Clark, and the engineer of the system was Atco. So Kubi performed the module installation and the DC and electrical installation. So we're installing all the panels on the racking system, and we interconnected everything. And so this project is in Red Deer, obviously, and it coats three faces of the building. The west, south, and east face are all covered in solar panels. It interconnects into 6 string inverters. In total, there's 545 295-watt modules, which at the time of construction was some of the best available. And now these days we're doing panels that are at over double that size. But 545 pieces of photovoltaic glass and approximately 50 pieces of dummy glass, which is glass that is meant to look like the surrounding photovoltaic panels, but doesn't actually generate electricity, isn't interconnected into the system, but it matches the aesthetic. So this project overall, just under 161 kilowatts DC. And so this project was completed using standard solar panels, just like the initial one there that Sydney was sharing. Standard solar panels onto a racking system with a typical siding underlay. Nowadays, there's products out there that can do this differently, that are more meant for the application. And looking at some of LMX's products, that would have been very handy for this project. So here's an image during construction. You can see it's very typical siding construction. You have your underlay, you got your insulation, you got your Z girts, and then on top of that was uh, solar PV racking and solar panels installed over the top. So this one was using typical solar panels, uh, and it coating every single side of the building. The construction was completed largely working off of these zoom booms and man lifts. So nothing too revolutionary there, just standard installation in that regard. One thing to note is that the tolerances are very important, as you can imagine. You know, if you're off by one inch or quarter inch on one side, you're going to be off by 2 feet when the other side hits. So hitting your tolerances is extremely important with BIPV and intricate interconnections like this. Here's an up close image of some of the more intricate pieces of glass. You can see all of the angled pieces needed triangular cuts or even irregular shapes. There's some small rectangles. There's some really weird shaped triangles, very small ones, very big ones, but they all formed part of the cladding system. This is what the finished product looked like, which I think is incredibly stunning. I'm pretty sure it won a few architectural awards, although Reimagine could comment more on that. Uh, yeah, like I was saying, one of the major challenges here, as you can kind of see the scale, is hitting your construction tolerances. It's very easy to have errors build over time, or if one window is off by a quarter inch, it throws off many more sub-trades in this aspect. So it's incredibly important to have precision when doing BIPV systems. The next project is one of Alberta's most iconic buildings. This is the Edmonton Convention Center. This was built by Bird Construction. The architect here was Dialogue. The glaziers on the system was Flynn, and the engineer was Gordon Howell with Howell Mayhew Engineering. Kubi completed the module interconnections and the DC wiring up to and including the inverters. And I gotta say, this job was crazy. It I can't really fathom a more difficult installation than this one that I'll get into here in 2 seconds. If you're familiar with the building, you know what the roof looks like. If you're not, the roof. This job was completed because the roof of the Edmonton Convention Center was due for replacement, and the roof itself is just under 100 meters long, cascading down roughly 4 stories along the Edmonton River Valley. The interior is a large atrium with roughly 50-foot high ceilings. The roof itself required around 645 integrated glazing units or pieces of solar glass. There was another roughly 74 pieces of dummy glass that were non-generating pieces of glass, which you can see a small glimpse of that if you look at the top. There is a circle pattern, and it's actually a Morse code inscribed using solar cells in the glass that read out a poem. And so all of that circular section was non-generating dummy glass. There was around 27 different types of glass of varying electrical characteristics or size that made up the project. It was just under 170 kilowatts DC, 150 kilowatts AC. And each piece of glass weighed up to roughly 300 pounds. This is a good shot of the building from the exterior, so you can really see the scale of it. Six or seven different cascading levels coming down down the river valley. From the tip of the north face to the bottom of the south face is roughly 80 meters. And now you can really see the slope and azimuth combinations that made this one so complex. And if you're not aware, electrically, you can't just connect any two adjacent solar panels to each other. You have to match them with similar slope and azimuth and electrical characteristics. So the flat section of the lowest row had to meet the flat section of the second row. The angled west section had to meet the angled west section of the row above it, and so on. The job was particularly challenging because it was completed in winter. Winter 2019, 2020. It coincided with some high school graduation party, so there was often herds of drunk kids wandering about into the work site. And most of our work was completed from the exterior. So we were up on the roof for the majority of this. And then, as you know, in 2020, the pandemic hit, and that tossed a giant wrench into everything. Another big aspect of this job was the weight of the glass. So the weight of the new photovoltaic glass was significantly higher than the original glass that was installed, and that demanded that the structural members of the building frame get upgraded. The job was also completed in stages. So scaffolding was set up along the interior and exterior. And as the job progressed in quarter sections, the previous section scaffolding was taken down. So the only way to go back and correct previous work was to scale up the outside of the building. So you had to take really special care not to forget anything. Otherwise, you're hiking up a 100-meter glass wall in winter. You know, the glass being roughly 300 pounds, I mean, you can't just have a couple people haul it up a ladder into place. This required spider cranes on either side of the Edmonton Convention Center, and each piece was craned into place where teams of glaziers then placed it and weatherproofed it, and our team of electricians came in to do the interconnection with the adjacent modules. Being a roof replacement as well, you can't just take everything down and then install everything. You have to do this step by step so you don't leave giant holes in the roof for extended periods of time. So that made it a rather tedious process. One thing to consider with BIPV that's different than any other kind of facade or glass system is wire management. Architects and engineers pay special attention with BIPV projects because now you have to account for wires running through the system, which is not typical with glass facades and roofs. So this project had wires running on the exterior through designated wireways, and you can see all the panels would eventually come together near the bottom on this south facing. You can see our now general manager Simon looking quite stressed out about all the wires he has to deal with. But to Sydney's earlier point, this is a really good example of working with the authorities having jurisdiction to make sure that they're comfortable with the new technology or the new techniques that are being used, because often interpretation is required. So the sooner you can get on good terms with them and outline all the safety considerations you've taken care of, the better off the project will be. Here's a few more random construction images that show the scale of the project and give a glimpse into the logistical challenges. On the bottom left, you can see the scaffolding that's roughly halfway down before the final stage was built. On the top right, this is actually on the north-facing roof, which, as Sydney mentioned earlier, you can certainly use north faces if you need to. They're not going to produce as well as south or east or west, but if you just need that little bit of extra energy, or if it wouldn't make sense to not have the north look the exact same as the south or east and west, then by all means, you can definitely use it. So this just shows the crane hoisting all the glass into place with the glaziers doing their thing, sealing it all. some of the big lessons learned on this one was uh, if you can, try to not do such a project in the winter. Uh, if you do have to do a convention center project, to try and avoid a high school grad season. Pay special attention to wire management. It's a relatively minor scope, but is critical to the aesthetics and the function of the array. I definitely recommend string inverters versus microinverters or optimizers, strictly due to a maintenance perspective. If you have lots of microinverters or optimizers, they're going to fail, and now you have to access some really hard to reach places on walls or on roofs. So string inverters, if at all possible. And lastly, you need electricians and an electrical permit. This is now an electrical system, and you need specialized trades to do this. We recently had to bow out of a prominent BIPV tender because we were asked to take over another contractor's work who was not an electrical contractor, and it was really unknown. So engage electrical contractors early for this because you can't just have uh, glaziers doing all the electrical work. There's major safety considerations when you have high voltages and amperages. So that was that project. I'm going to go through a couple more slides that showcase some BIPV applications. This one's not technically BIPV, but it's kind of BIPV adjacent. This is a project we did using Mitrex glass. And so these panels were coated with a shingle image to allow them to blend in seamlessly with the roof. And this just showcases that solar can be much more than just standard blue square cells on a white background or a glass background. You can have it custom matched to really any image, any shingle type. Moving forward, these are some images from LMX. Once again, these showcase that solar is more than just standard looking, blue and black cells. You can have you can have the crystalline look like you can see in the top left, where it looks like a solar panel of um, varying size, varying number of cells per piece of glass, or you can have rather opaque looking glass or solid looking glass that doesn't necessarily look like a solar panel. One thing to note is that if you look at the top left, you can actually, with solar glass, you can actually customize exactly how much light you want to come through the building. So you can space out the cells more or less, depending if you want more energy production or more light to shine into the building. This is an example color range from LMX as well. So you can see there's a wide range of colors that you can do to match really any building aesthetic. Each color is going to come with their own power density. So they're going to range anywhere from roughly 50 watts per meter squared to 180 watts per meter squared. Naturally, dark blue and black can generate more than white or sand. These are a couple images from Onyx Solar. Onyx they were the glass supplier at the Edmonton Convention Center, and they're a big BIPV manufacturer as well. These were not Kubi Energy projects, but I just wanted to include them to showcase what BIPV can do in different areas. So on the left is a crystalline glass facade where you can see the solar cells. Like I said, you can customize the spacing as well. So if you want more light to come through, very achievable. And on the right is amorphous glass or solid glass that doesn't look like a solar panel per se, but it does generate electricity. This is Mitrex's head office. They are a Canadian BIPV manufacturer, and I had the pleasure of touring this a few years ago. And this is a really good showcase that BIPV can come in any size, any shape, any color, varying textures. The options are quite limitless today with what you can do architecturally. Now, some numbers. So to outline the next few slides, I'm going to walk through a sample investment comparison. And keep in mind, these are rough estimates only. The numbers you see here are, once again, rough estimates only. I'm sure that it can be plus minus a fair margin. Uh, it's also worth noting that comparing BIPV to vinyl isn't isn't quite apples to apples. One's a more premium finish and the other is a value option. It's like comparing a Ford Focus to a Tesla Model S or insert any car manufacturer that you actually like. They're just different categories, and one has an arguably much larger aesthetic advantage. So I included ACM as the primary comparison, which is more on that level of premium siding finish. So some different costs. I have vinyl at $6 per square foot, scaling up to ACM at $30 per square foot, and BIPV panels ranging in the $90 to $120 per square foot. Like I said, these are all rough estimates. We can certainly drive that down below 90. Certain applications could be above 120. And using the color palette from the previous page, you can see the range is from roughly 30 to 180 watts per meter squared. So here's a annual cash flow scenario. This is hypothetical, and this is a approximately 500 meters squared vertical wall that is facing south in Calgary, Alberta. So 500 meters squared, roughly 5,400 square feet. I assumed it's going to produce roughly 1,000 kilowatt hours per kilowatt installed. And this is all facing south. If you have panels facing east, west, or north, you're going to produce slightly less. East and west in the order of 20 to 30%-ish worse than due south. I assumed a 15 cent per kilowatt hour, escalating at 4% per year to get this. This doesn't include labor. However, the labor will be somewhat similar for both standard cladding and BIPV cladding. BIPV, it's going to be slightly higher because a second trade is often required. This is where you need your electrical contractor. And there might be some additional engineering and architecture time for BIPV systems. And so what you're seeing here is the annual cash flow for a BIPV system at $90 per square foot. The capital investment is just under $500,000. And then every year after that, you're going to be making roughly 10K to 30K from the energy savings. Now this new line, this shows the cumulative cash flow. So this is the sum of all the little bars. And before you go taking screenshots, just wait. I'm going somewhere with this. You can see the green line crosses the x-axis in year 23, and that would be a full return on your investment. Since it's ballparks, call it 20-25 year range. But what I didn't mention is all the grants and incentives that are available. There are a couple really good ones and possibly more on the way, especially with our recent change in federal government. As you're all aware, politicians like to put their own branding on things. So some Carney bucks might be on the way. If there's anyone from the federal government here, you might want to workshop that name. But the two main incentives right now are a 30% investment tax credit and an accelerated depreciation rate of 55% in year one. And that's as of 2026. So what do those two incentives look like on your annual cash flow? What those mean is you're going to be getting a big spike in year one from that 30% investment tax credit and your 55% depreciation allowance. Now things are starting to look a little better. Payback in 15 years-ish. That's nothing to sneeze at. Especially when you consider how long does a building need walls? Seems like a silly question, but if you plan on having the building for 30 plus years, then the system will pay back in less than half of its life. But it's one thing to look at payback on its own, but we haven't compared it to anything yet. And this leads to another question, which is, what's the payback of a standard cladding system? This one's not as intuitive to quantify, but what we can do is look at the lifetime cost of both products. And so here's that same graph with the ACM panel at $30 per square foot overlaid. And that system would run you roughly $170,000. Obviously, it's cheaper than BIPV in years 1 to 7, but the lifetime value paints a much different picture. Yes, you earn back 100% of your investment in year 15-ish with the BIPV, but you would have spent $170,000 on ACM cladding had you not gone BIPV, which would never pay back. And now you can really start to see the difference in the latter years of the project. So when you pan to the right of this image, you can see in say year 25, your system's actually made you a good chunk of change. In this example, $250,000. And so your difference after 25 years between the two systems is actually $420,000 if you add up the profit plus the cost of ACM that you would have done. So green line is option A, orange line is option B. One's a short-term investment, the other is the long-term investment. So I'll leave this up here for a quick second if anyone does want to take a screenshot. But I think it's just important to highlight the long-term value of solar. It does pay off, but it takes 10, 20 years-ish. And beyond that, there's some difficult to quantify architectural advantages. Like many of the buildings that Sydney was just highlighting are stunning, and you can't achieve that without doing some of this cutting edge technology work. And just for fairness sake, here's the hardy and vinyl cost comparison as well. As you can see, they're a much more affordable option. But even with that, in year 25 plus, you're still much better off with the BIPV. It's a huge long-term advantage, and there is a huge aesthetic advantage to BIPV. That's all I have for you. If anyone is interested in BIPV or regular residential or commercial solar power systems, please reach out to me directly or my team at Kubi Energy. Thank you very much.
Awesome. Thank you so much, Adam. And Sydney, if you could join us again, thank you. So we've got some questions coming in the Q&A, and I'm just going to remind everybody to put your questions in the Q&A box rather than the chat. And you can also upvote the questions so that we can get to the ones that are most upvoted. We might not get to everything today, so that's why I just encourage everybody to upvote. While people are putting their questions in the chat or in the Q&A box, I did have one question for each of you. Sydney, I was curious, you've been doing this for quite a while now, and I'm wondering whether the buildings you did back in 2017, some of those are only perhaps producing 20% of the building's electricity for the year, I think you mentioned. If you were to do the same one today, do you think that the technology has advanced to the point that it would be offsetting more of the electricity? For example, I think one of them was maybe 60% offset of the electricity. I mean, these are great accomplishments, but I'm just curious if you think the technology has advanced enough that you could get any of those buildings to net zero from an electricity perspective.
Great question. And I know Adam was talking about long-term cost, and aesthetics, but at a certain point, this really is about energy. And there's no question that the efficiency of these panels is improving dramatically year on year. I'd also just like to say that conditions vary over the course of the year. So even that first example, which was providing close to 20% of the electricity that was required on the building, was talking about what was required or what was a cumulative year-over-year average. The numbers really vary across time, particularly in the shoulder seasons. Even in that project, the cladding was typically providing somewhere between 60 and 70% of what was required overall. And there were days when the cladding system provided all of the energy that was required in the building. So when you think about these projects in terms of energy independence, opportunities to balance between different systems, there's a huge opportunity to draw on cladding. And yes, the technology is improving all the time, and so we only see those numbers improving.
Thanks, Sydney. I guess as a follow-up on that, Adam, I had a related question for you, which is the buildings, the Red Deer Polytechnic, the Shaw, what percentage are they able to offset of their building usage, on average? Do you have any ballpark figures for me on that?
Ballpark, I would say each of them is probably in the 5 to 20% range, but that is complete ballpark.
Mm-hmm.
And I'd also add the caveat that the RO the percent offset doesn't really affect the ROI.
Mm-hmm.
Whether you spend
No.
$100,000 and offset 5%, that means if you want to offset 10%, you have to spend $200,000. So
Yeah.
there's some economies of scale, but the ROI is going to be roughly the same.
Yeah, I appreciate that nuance. I guess I'm used to hearing a lot about residential, where getting to net zero is obviously a lot easier than in a commercial setting. So it's really helpful for me to understand what things look like on these commercial builds, and just how much more difficult it is to accomplish. I should say getting to net zero electricity wise seems a little bit easier on a residential scale, from some of the stories I've heard. So it's really great to hear about these commercial builds. Okay, question here from Adam Stoker, for both of you. The question is, where were the inverters located on the projects that you presented today? Maybe Adam, do you want to start with that?
Sure. Yeah, at the Red Deer residence project, the inverters were located on the roof, and we positioned them as close as possible to the edge to stay within the 1 meter requirement to negate rapid shutdown.
Okay.
Very similar strategy was used at the Edmonton Convention Center, where the wall comes down and meets. There's a south wall and a little landing that's inaccessible to the public. The inverters were placed there once again within 1 meter of the array to negate rapid shutdown requirements.
Oh, interesting. How about for you, Sydney?
I would say with one exception, typically outside, the Canadian Science Museum used microinverters, which are located inside the building. But in every other case, as in Adam's experiment, the inverters were located at rooftop level. So that means we were able to keep all of the cabling outside of the building envelope, really uh, minimizing openings, penetrations, and sort of complex detailing of cutting through the building envelope. And that meant we could also keep the inverters, the combiner boxes, and so forth at rooftop level, very close to our mechanical penthouses, where the main point of transition would occur between the exterior cladding system and the interior power systems for each one of those buildings.
Okay, super helpful. Thank you both. Anna Maria is asking, well, first, thank you both for great presentations, and I agree with that sentiment. So Anna Maria is wondering if in any of the BIPV projects you presented today, whether you faced any issues with insurance. And I suppose that wouldn't be something you'd necessarily have to overcome. I imagine the building operators would be having those conversations, but did you hear of any issues with insurance for the building operators?
That's probably a better one for Sydney to answer. We would come in and do the installation, so we didn't really deal with the owner's insurance requirements too much.
Mm-hmm. Sydney, any thoughts on that?
No issues raised in terms of long-term insurance. There were, as Adam said, these are complex systems, and in some instances, we did have to go through extra steps with building authorities prior to installation or prior to commissioning of the systems, and that that required alternative compliance systems, or sort of alternative compliance solutions with regard to local building codes. So some complexities for certain, but not anything I'm aware of that was a consequence in terms of insurance.
Yeah. On a similar topic, I was curious, you mentioned having to work with those local building code folks and different variances and whatnot that were required. Are there any jurisdictions that you folks find easier to work in than others? We're just always looking for best practices. And when people always say to me, well, what jurisdiction should we be like? And I'm just kind of curious who you prefer to work with, just given their approach to these matters. Adam,
That's a
you're
loaded
kind
that's a
of
loaded question. I don't want to
smiling there.
name names publicly.
No, don't name people, but just jurisdictions.
Lots of areas in Alberta are easy to work with.
Okay.
I'll give a politically correct answer to
Well,
that
you
one.
know, and that's consistent with what I've heard at the Canadian Renewable Energy Association meetings when I meet with solar folks from across the country. Even though we have issues in Alberta, they generally find it a little easier here to navigate some of the systems than elsewhere in the country. How about you, Sydney? Do you have any preferred jurisdictions?
A couple comments. First, well, it's a first in almost every case. There will be some familiarity with ground-mounted systems or roof-mounted systems, but BIPV is a bit of a different combination. And in our experience, there's been a huge interest, huge willingness to try to figure out how these projects can move ahead. And it was really interesting, really encouraging for us to see in the Winnipeg project that as a result of working on this project, the city then developed their own sort of how-to guide and an extra steps, a recommended process form that they posted online in order to help others who came after us figure their way through these kinds of projects. So I think overall our experience has been really positive, and there's been a lot of interest in each of the jurisdictions we've been working with.
Yeah, I suppose it helps that many of the projects you two have listed are in some way government funded, whether it's a government institution itself or a municipally controlled corporation or something of that nature. They would obviously want to see things move ahead wherever you're working in that sense. It would maybe be a little bit more challenging if it was just private sector leading the way on this without any government support or involvement there. So. Interesting to contemplate. Jerry's wondering here, will the pilot group host a training session for electricians? I don't know what Jerry's referring to there. I'm wondering if you know, Adam?
I don't know what the pilot group is, sorry.
Yeah, I don't know either. Do you know, Sydney? Okay. I'm not sure what the pilot group is, Jerry, but you can add more to your question in a subsequent question if you have a minute. Thanks for checking in on that. Here we go. Dave's question. Adam, did your cash flow payback on BIPV take into account maintenance expenses? I think of the possibility of a bird strike or extreme weather event. I was actually thinking the opposite of Dave. I was thinking neither of you commented on how much more durable solar is than most other products and how actually you're probably saving money when it comes to durability, but maybe I'm wrong. So let's hear your thoughts on that. Adam, you want to kick us off?
I think you're right. It's hard to say because I don't have a lot of data on these BIPV panels in action over 20 years and how much maintenance they would require relative to a standard solar panel. To answer your question directly, though, I did not include maintenance expenses, but I would assume that bird strikes or extreme weather events wouldn't impact solar any more than they would a standard cladding system.
Sydney, thoughts on that?
Just trying to think of examples from our portfolio, and maintenance has been to date pretty straight, really actually quite limited. And I think that's what I was trying to get at in terms of that slide where I'm showing like the simplicity of a BIPV system compared to the complexity of the different mechanical systems that they interface with. So relatively speaking, they're some of the simplest systems that we work with in the overall energy picture, and not, I would say, not significantly different um, from other cladding systems, or even the window glass nominal cleaning, depending on the kind of glass cladding that you choose. But overall, there are no moving parts. And our understanding is that over time, it may be, the junction boxes on the backside of these panels may be the first thing that will require attention. But typically, one of the real benefits of these systems is that you can track the output of every single panel that makes up the full array. So you know immediately if there's any kind of issue with individual panels. And so you're able to identify, track, and go back and make adjustments as needed on a panel by panel basis.
Yeah, it seems like the modular nature of solar would be really helpful in terms of making things fairly easy to maintain. You don't have to deal with them. It doesn't mean like just because one panel is not producing doesn't mean that they're all not, right? So it's nice that you can track them all.
To add to that, that's why I stated a recommendation to use string inverters instead of an optimizer system or a microinverter system to reduce the maintenance potential. If
Mm,
something's going to fail, it's most likely going to be an optimizer or a microinverter. That'd be very hard to reach on some 40-foot high facade or roof.
right, good point. Okay, Dave's got another great question here. Let's see, Sydney, question for you. What conversations were had with building owners about BIPV and the need for more planning in relation to future facade access versus a standard EIFS panel or a glass panel, which requires very little maintenance? So I guess relating to the maintenance question from earlier, but conversations with building owners about that. How did that go?
Think that's one of the reasons why we're quite careful to develop mock-ups for each one of these systems in order to work through with the installers any questions of detailing that will sort of minimize construction issues, water shedding issues over time, and so forth, and also to be able to demonstrate to owners a really good understanding of what the components are, and again how relatively limited the maintenance is for these systems. But should it be required, again, what's involved in taking off a single panel? Each panel has its own connections, its own connectors, and so the access and replacement to any one of these is relatively simple. And in just about every example I showed, installation is being done by a bucket from grade. So the opportunity to bring in equipment to access these facades is pretty straightforward as well, given the scale of these projects in terms of construction. Every one of these at any height has a system of roof anchors that has to be provided in order to access exterior cladding of any kind for maintenance and repair over time.
Mm-hmm. Okay, thank you. All right, another question here for you. Since all PV systems have characteristics relating to visual, structural, and electrical elements to them, what is one of the most significant design considerations when designing BIPV systems in particular? So maybe I'll go to you for that one, Sydney. What do you have to think about the most? I remember in your presentation, back in the day, you really had to think about the building in relation to what the standard size was for a module, but that seems to be something you can kind of get around a little bit now today. Is there anything that's still really top of mind when you're designing with BIPV in mind?
I would say a number of considerations. Of course, we're looking at context, what kind of exposure conditions there are in terms of building orientation or shading by adjacent structures or trees or so forth. Just what are the kind of fundamental opportunities for sunshine on the building? But as we move from one project to the next, I would say that the consideration that also warrants quite careful quite careful review is the choice of glass, the choice of coatings. Adam mentioned a range based on color. Depending on what color you choose, the output will vary, but it also varies considerably depending on the kind of coatings that you work with. So, for example, the chromatics glass or other PVD coated glass that Solar Lab brought to us for some of our earlier projects is still kind of a gold standard in terms of energy efficiency, and depending on what glass source you are looking at, what the coating type is, what the color and pattern is, there can be a significant change in output. So when you think about those, in the end, this is really about energy. It's not just about what it looks like. It really is about energy. And so those graphs that Adam was showing can vary considerably depending on the choice of glass. So we want to make sure we've got the most effective, efficient glazing components that we can, and then we also look at what the capabilities are within the local construction market. Who's putting these up? Is it someone whose background is in photovoltaics? Is it someone whose background is in cladding and flashing and those aspects of a building envelope? So it's a combination of a number of different technical considerations, but I would say largely it's the choice of glass and who's available to install and detail the system.
Yeah, that's a good point, Sydney, because you work in many different jurisdictions and not all of them have as much expertise as we do here in Alberta. So I appreciate that point on who's available. We have 150 business members, so we kind of have a plethora of availability here in our major centers, but I imagine that's not the case in other jurisdictions. So thanks for making us aware of that. Adam, any thoughts to add on Sydney's comments there?
No, that's a good summary. I think aesthetics is always a huge one, but also just how much energy you want it to produce. That's gonna really, and how much area you have. You know, if you have a small area but you want a lot of energy, you're gonna need a black or blue, more high power module.
Right.
If you don't necessarily need the energy, it gives you more flexibility. If it's just a nice add-on.
Yeah, it's interesting how that's really, beauty's in the eye of the beholder, because we were just recently doing an assessment of different jurisdictions in Alberta with respect to solar. And, Banff has this bizarre requirement that your modules have to kind of match the roof or something like that. And I just thought, what a shame, because I love solar and I love knowing it's there. And so for me, when I see a nice array that maybe doesn't match, I find that more striking because I love solar. And so I would be, really sad if I had to put up a hidden array so that nobody knew, because to me it's like, no, let's celebrate this wonderful advancement in our community. So, but I do appreciate that different communities have different regulations with respect to the color as well. So the gold coloring, I loved that, Sydney. I thought, oh, I wish I could have had gold on my on my garage here. Anyways, that's pretty beautiful. All right. Oh, Mark's here today, one of our teachers. Hi, Mark. His question just dropped down. I gotta grab it again there we go. Can we get a description of the framing of the modules to ensure water wind sealing? So question about water and wind sealing. Any thoughts on that, Adam?
I would say the best thing to do would probably look at LMX's website, and they would have all of the sections and how their system clicks together to create that. And it would do a much better job than me trying to describe it.
That's fine. Yeah, it's good. As long as we have places to go for more information, I think that's very good. All right, Daniel says here, what can be done to make BIPV more widespread and economical? That's a good question. Like, it's nice that government is involved, but wouldn't it be nice if they didn't have to be, constantly sponsoring the new builds? What are your thoughts on that, Sydney? I'll maybe start with you and then we can jump to Adam.
Another super question, and that's a real question for us as well. I mean, we're really interested to work on each one of these as individual projects, but in the end, the goal is much more widespread adoption and better understanding of what's there. How do we scale these things up, and how do we scale them up more quickly? And I think be one of the simple answers is to be able to share what we've learned and to take advantage of opportunities like this to explain what's involved in these projects. So I would say organizations like Solar Alberta make make these things more widely understood. The more exposure we can give for these projects, the better understanding there is. As you learn, uncertainties can be put aside, and the opportunities of these projects become better understood. So, sharing what we know.
Yeah, thanks, Sydney. I heard that in Europe, apparently solar costs much less than in North America. And so apparently it's cheaper right now to put in a fence that's made of solar than of wood in some jurisdictions. I thought, how do we get to that point where we can just put solar up as our fencing and whatnot? Because that's really the dream, isn't it? Adam, further comments on how to make this more economical, this conversation?
Yeah, scalability. It's kind of a catch-22. The more that's out there, the cheaper it's going to be. So it's going to start at a very expensive level, and then the more people do the projects, the more companies get involved offering products, more people get experienced installing it. It's going to drive the cost of it down, and the overall system is going to go down.
Just like with traditional PV, hey, it's just gonna
Just like with traditional
it'll
PV,
follow
yeah,
that
yeah.
path eventually, just a little
Economies
slower.
of scale. Another thing that would help is if you pair it with rooftop solar. Rooftop solar is still going to be the best ROI for solar out there on the commercial side. So, you don't just have to do BIPV. You can load your roof up with a 100
Mhm.
kilowatt system, and then, your 50 kilowatt facade, you now don't have to bring out a second contractor or engineer to deal with that system.
Yeah, no, lots of possibilities, and I've heard the price of batteries is starting to follow that the same trajectory where slowly things are getting more affordable. So hopefully in 10 years we'll be saying, wow, the price of BIPV and batteries has dropped by 90%, just like just like we get to say with solar PV. So the traditional style. I have to get up on the lingo that you guys were using today, so because it's important to be able to differentiate between which solar you're talking about. So, well, we're at the 1.5 hour mark time frame, and I know we've got more questions here. So we didn't get to everything today. I just wanted to encourage you to reach out to Sydney and Adam and their respective companies. If you've got other questions, I know Sydney and Adam might not themselves be able to respond, but there's a lot of expertise within your respective companies. So do that. And if folks have questions for Solar Alberta, you can, of course, always message us at office@solaralberta.ca, and we can try and nerd out and get some of the answers for you as well. So I just wanted to give a huge thank you to Sydney and Adam today. That was just amazing. I've learned a lot, and this has been a long time coming, this presentation. We've been mulling this over for a while, so thank you for making it happen. And of course to LMX for sponsoring this. We couldn't have done it without them too. So I really appreciate you all and our extremely engaged audience, including some of your colleagues and coworkers and competitors. So it's very nice to see everyone in one place and learning and growing from each other. So thank you to all for attending, and have a wonderful rest of your day.
Thank you.
Thank you.